this. I think this morning everything was on. And better like this. Thanks.
Yeah, so just to start, I wish to thank the organizers for the invitation to come and give this talk. In preparing the talk, I made two assumptions. The first assumption was that I was going to be the eldest speaker at this conference. And if I look around, in fact, I wasn't wrong. That was the first assumption. And being the eldest, I thought that I would give a talk about the quark masses in a slightly different way as I expected to be given by my distinguished colleagues, as they did. I went into all the kind of details. So my talk is slightly different. I will emphasize the history of the quark masses starting from the very beginning, that is, before QCD. So because quark masses existed before QCD. That doesn't sound right, but I'll explain why. All right, so that is the introduction. So let me start moving this thing up. Yeah. So the first thing about the quark masses that is not widely known fact is that the quark mass is a fractal. You know, fractals are objects that don't scale linearly. They have a non-integer dimension. So in fact, if you look at the fractals, so how do you move this thing? Here. In fact, the coupling, of course, scales like the log, but the mass does not scale like the log. There has the so-called anomalous dimension, and therefore it becomes a fractal. So that's something that is quite interesting to know about it. I will give them a short history of the quark masses before QCD. They were known already before because we had the symmetries of the strong forces involved in the weak interactions. So we start with Heisenberg that invented or discovered, depending what you want to say, SU2, and then we go from there to Gell-Mann with SU3. Okay, and then of course the fundamental representation is void. We know that. We knew that then. People tried to discover quarks, but nobody succeeded. There were a couple of papers when I was a student of two guys that claimed to have discovered free quarks. I mean, in those days there were no free or not free. I mean, they were simply quarks. And then of course those results were wrong. So the quark masses enter then through the hadronic weak interactions, and then that was a subject called current algebra. And we moved from isospin from SU2 to SU2 vector times SU2 axial. So that was a chiral symmetry. And the same thing happened to SU3. We generalized SU3 to a chiral symmetry now. And then the generators of these symmetries are the vector currents and the axial vector currents. And so that is where the quark masses made the first appearance. So let's take a look at the pattern. We start with SU3 cross SU3. The divergence of the vector current is proportional, or involves the difference of the quark masses, ms Lestrange minus MUD. So in the chiral symmetry, all these three masses are zero, and therefore that SU3 cross SU3 has a conserved vector current, as well as a conserved axial, because these masses are also zero. So in that massless limit, SU3 cross SU3 is an exact symmetry of the strong force in the weak interactions. So now we want to break the symmetry. So we will proceed in steps. The first step, we will make the strange quark mass non-zero, and then keep mu and MD equal to zero. So now the divergence of the vector current is proportional to the difference of the masses. So if MD is equal to mu is equal to zero, the vector current is still conserved, but the actual current is not. So we go from SU3 cross SU3 to SU2 cross SU2 plus SU2. So SU2 is still a symmetry of the problem. And then we make the second symmetry breaking. Now we make MS different from 0 and MU equals to MD different from 0. Then we get down to SU2. And then finally we make MU different from MD, different from 0, and we end up in U1. So that is what we knew in the late 1960s. That was the scheme. And there was an alternative scheme that gave different predictions, but eventually that alternative scheme proved to be in disagreement with experiments. So that is what survived. Right. So in the absence of course, we didn't have a theory because we didn't have a Lagrangian. Okay, so a theory is defined by its Lagrangian. So we only could determine quark mass ratios because if there was a theory there would have been an infinite theory. We didn't know about renormalization or anything because we didn't have all the tools to do that. So we could eventually only determine quark mass ratios, and that is a topic that slowly progressed and is now called chiral perturbation theory. In those days, we didn't call it like that, but that's what it was. And what we could do in those days was to relate the ratios of quark masses. We expected that whatever infinities there were in the masses will cancel in the ratio. We related those ratios of quark masses to hadron masses, and some weak interaction processes that depended on that ratio. So then we could determine at least the ratios of the quark masses. That's the first attempt to get to the numerical values. So the strong interaction Hamiltonian in those days was written in this way. There was some sort of symmetric object here, trivial, and then there was symmetry breaking terms, epsilon 8 that breaks the SU3, and then epsilon 3 will break the SU2, and then we end up with U1 over there. So the ratio of quark masses, I mean, these quantities, of course, these densities were infinite. We didn't have a Lagrangian. We didn't have a theory. And therefore, these things were infinite. But we expected that when we took the ratios of these quark masses, these infinities will go away. So that was multiplicative renormalization, which for the young people today, that would seem obvious. It wasn't obvious because I remember once I gave a talk at Los Alamos, and I was talking about this thing in multiplicative renormalization, and somebody said to me, yeah, but how about additive renormalization? I said, what are you talking about? And then there was a big discussion, and there were people in the audience saying that I didn't have the right to assume that renormalization was multiplicative. So now, of course, nobody will say that, right? We will kick him out of the room. So anyway, that's the situation. So for example, the ratio of the up and the down is a number that we could write it down in terms of the masses of the kaons and the pions, and then that ended up with that value there. And then we had an MS over MD, for example, to be about 40 times bigger than that. So that was sort of a rough sort of determination. There were processes, weak interaction processes like KL3, the KL3 decay, that were sensitive to the quark masses, and therefore we made a prediction for the ratio of MU or MND. That comes straight from there without knowing QCD, of course, in those days. And then there was another one here as well, the ratio of MS to that. This subject is now topical because it's what is called now chiral perturbation theory. Chiral perturbation theory was born there with these things I just explained. And chiral perturbation theory is a very active field in which people determine these ratios with very high precision. The actual number today, by the Flagg collaboration, that's last year, 2 years ago, that number had a very large error, obviously, but that's what it is now, and this one is 27 instead of 29. And there's another relation which is called the Q relation or Q-square relation that involves the ratios of the masses of the kaon and pions, and then, this ratio is determined today by the Flag collaboration to be, involves these quark masses 28.1 plus or minus 1.3. In those days, we looked at the decay of eta into 3 pions, at weak decay, strong interaction weak decay, that we made this prediction with a very large uncertainty, and now the Flag collaboration is that. So that physics that was done in those days evolved into what is the subject covered by the Flag collaboration, which is very important because it gives us independent information about the ratios of the quark masses. So now, of course, we know eventually QCD came into the game. So we have now we had a quantum field theory that was renormalizable and so on and so forth. And then, of course, the quark masses were there in the different guise. The question is, of course, how do we determine, now we can determine the individual values of the quark masses, not only the ratios. So we have to relate somehow QCD to hadronic physics. They are valid in very different regions of energy, as you know. So how do we relate them? Well, one way of doing that is by going to the complex square energy plane and making use of Cauchy's theorem in that plane. You know, if you have a complex function in the complex plane, whatever the plane is, they are very restricted. The Cauchy theorem is very restrictive. There are many things that can happen and many other things that cannot happen. Okay, so that is one of the ways of relating that to that. Obviously, there is a parallel approach, which is based on getting a supercomputer. You put in there the QCD Lagrangian, and you ask what is the mass of the proton. You come a year later and tells you 900 MeVs, but you don't know why that is the case anyway. So that is a numerical approach. We like this approach because at least we can step by step try and understand what are the different components, what are the contributions of the different components into the game, both from the QCD side as well as from the hadronic side. So that is the idea, to look at the squared energy plane, which is shown here. That's the real part of S is the square energy. We have here the real axis, and then we have a circle, let's say an integration circle. And the hadronic physics, the hadrons live in here. Stable hadrons live along the axis, and the resonance is on the second Riemann, on the second Riemann sheet. And but basically along this line is the hadronic physics. And if the radius of this circle is large enough, then we can invoke QCD on the circle. But Cauchy theorem relates what happens on the circle to what happens on the axis. And therefore that is a very strong sort of a statement of a relation between two completely different dynamical quantities. And that's why some of us at least, are happy with this kind of interpretation. And so that leads eventually, I think I'm missing a transparency. This idea of the complex plane was proposed many years before QCD in the present form. But I mean, it was done in the 70s. And unfortunately, I think I missed the reference here. I had it somewhere else. Anyway, so the QCD sum rules start with the consideration of correlation functions. So we have correlation functions of currents, for example, vector currents or axial vector currents. In QCD, those currents are made out of quark fields. So you will have currents and then divergences of currents, for example, the divergence of the axial current. involves the sum of the masses, and then the divergence of the vector current will involve the difference of the masses. So there's the representation in terms of the QCD degrees of freedom. And then once we have that, we can invoke a Cauchy's theorem and then relate that to hadronic physics. Okay? So basically, to continue with the QCD part, we will have the perturbation theory. Perturbative QCD will be this unit operator, and then we will have vacuum expectation values of operators that are built from the quark and the gluon fields of QCD. So we know, for example, up to order alpha to the fourth, some of these correlation functions, others up to alpha to the third. And the important point is that the Wilson coefficients multiplying the vacuum expectation values goes down with Q squared, with momentum transfer, 1 over Q squared to some power. So among the best known object sizes, the quark masses and the gluon condensate. Those are quantities that appear in this relation. So we will have then all that representation for QCD in the complex plane as well, and then relate that to hadronic physics. Just to give you an idea of the state of the art, if you know the quark mass at some scale, you can determine the quark mass at another scale up to the order alpha to the fifth. So this is it. This is how far we have moved in terms of precision. Okay, sometimes you know the quark mass or the coupling constant at some scale. You want to know it at another scale. There's a similar expression, of course, for alpha s, and that's amazing. That's amazing how far we have moved. So going to the hadronic part, there are channels in which you have poles. For example, the pion pole is a strong interaction, is a stable particle for the strong interaction. So the Capen pole that will saturate the divergence of the axial current. So you will have that, and then you will have excited states and resonances. And then Cauchy's theorem is going to relate the two representations for us. This is a typical sort of drawing of a spectral function, a hadronic spectral function. You have the pole here, the pion or the Capen, and then you have resonances. And then eventually this continuous line here, the curve here represents the QCD part. Some energy squared where perturbation theory becomes valid, then QCD will be given here, and hadronic physics will be given there. And this brotherhood is going to be enforced in the complex square plane. This is an example of the pseudoscalar channel in which you have a pionic resonance, a 3-pion resonance here, and then another one over there, and then eventually this thing becomes this. So unfortunately, what happens is that these hadronic spectral functions, in particular in this case, cannot be measured directly. So there are some data and some very good predictions from chiral perturbation theory at the threshold, but after that, this is model dependent. So and somehow, when you are going to use this framework, you have to be cognizant about that fact, and that, of course, will introduce some uncertainty into whatever determination you are trying to do. So basically, we start then back to the complex plane. You have Cauchy's theorem in here, and then you split the circle and separate it from the axis. So you get then the contour integral and the line integral. Here is the hadronic information, and over there will be the QCD information, and that is how the sum rules start to work. Okay, so now, for example, in the case of the light quark masses, up, down, and strange, the perturbative sector is known up to alpha to the fourth, and then we know the quark condensate quite well, and the gluon condensate is improving its accuracy over time, but it still remains a quantity that has to be it has to be studied, try to be determined with more precision in the future, it is in some channels a very, very important contribution to the results. And then, of course, in the hadronic sector, we have the ground state poles, which are the pion and the kaon, for instance, and then the resonances and so on and so forth. And then we have a chiral perturbation theory that will allow us to somehow say something about the resonances at threshold. And that's something that at the beginning nobody paid attention to, and eventually it became clear that one has to do something about that, and that was some historical determinations of this use of chiral perturbation theory to determine the threshold behavior of that. So basically what we end up with is, in terms of the quark masses, a ratio of quantities that are hadronic, involve hadronic information, and QCD information. Now, the problem is that, at least in the case of the light quarks, the perturbative QCD convergence is very poor. So this will be an expansion here. This mass will be proportional to some QCD expression that involves alpha, alpha square, alpha cube, alpha fourth, and so on. And the convergence is bad. So obviously that doesn't lead anywhere. You're not going to trust a determination in which each term is bigger than the previous one. So what do? Well, there's a mathematical tool. There's a mathematical tool which are called the Padé approximants. If you introduce these Padé approximants, you can seriously increase, or just make this problem disappear, more or less, and end up with predictions that are sort of nice. They are definitely much better than just simply get the mass from this ratio here. Padé approximants is the name of the game. Okay, and that covers more or less the light quarks. And then for the heavy quarks has been one of the channels that has been used as the vector current correlator. So we have in the QCD sector, perturbative QCD, we know up to alpha cube, and then the gluon condensate is involved in there. There is no heavy quark condensate that is related to the gluon condensate, so there is no such a thing. So there's the only non-perturbative contribution comes from the gluon condensate. And in the hadronic sector, of course, we have good experimental now, because for the charm and the bottom, we have good experimental information from E plus, E minus data in the J-psi for the charm, and in the epsilon region for the bottom. This is, for example, I think you have seen it from other speakers already, E plus, E minus 2 hadrons. This is information that you can feed into the sum rules in order to get the quark masses. So now we have the results. These are from some determinations, and comparing the masses, the quark up, down, strange, charm, and bottom, comparing with the particle data group or the lattice QCD. So these two are from lattice QCD, and these are from the particle data group. So you can see the up quark mass is 2.6, plus or minus 0.4. This is the PDG value. The down is 5.3, 4.7. This is quite an interesting difference there compared to the up. It has probably no dynamical origin. It's probably something that has to do with the numerics that seems to be, but they're still within limits. And the same story with the strange quark. The charm quark here is very good prediction, and the bottom is two are from lattice QCD, and that is from the particle data group. So I think we have reached a very, very sort of nice and reasonable sort of environment or situation in which we can use QCD and hadronic information to determine this set of quark masses. Reference to other recent quark mass determinations will appear in the written version, especially those from the speakers that are sitting here. Okay, so I didn't put that there, but I promise you, you all will be rewarded for your efforts. And just to make an advertisement for this little book, last year Springer approached me. They have a series of thin books, about 100, 150 pages. They wanted me to write a book about sum rules, and I thought I would never write a book in my life, but they insisted. So now that book is available. So if you want to take a look at that, you can. Actually, it's very funny because you can download not the whole book, but you can download the book by chapters or something crazy like that. Anyway, so that's where I come from. This is Cape Town, South Africa. This is the Riviera here where all the multimillionaires live. So I am not living there. And then the university is on the other side. This is Table Mountain here. And then on the other side is the University of Cape Town. This is the Atlantic Ocean, and that is the Indian Ocean. So when you live in there, you have to choose in the morning, on a Saturday morning, in which ocean you want to go. Okay. That's all. Thank you.
At some point you said that the perturbative QCD thing multiplying the quark mass was not convergent. Can you in one of your slides you said that the perturbative QCD expression multiplying your quark mass was not converging very well. Can you elaborate on that?
I can't hear well with the speaker.
He's talking about your slide about the convergence of the perturbative series.
Oh, yes. I didn't go into details, but the detail is in the papers. You have a ratio, okay? So maybe we should go back, because that's a very important question here. Yeah. So you see, this ratio involves here information about, let's say, for the light quark, let's say F pi, right? And the mass of the pion and the resonances, they're all in there. And here you got QCDs. You have 1 plus alpha s plus alpha s squared. Now, is 1 over that. So bring these things up. So it will be 1 minus minus minus. And then when you look at those numbers, they're all the same.
My question is, do we know why?
Eh?
Do we know why that happens?
It's a peculiarity of the pseudoscalar correlator. If you look at other correlators, that doesn't happen. It's just the fact that the Wilson coefficients of the perturbative part and the Wilson coefficients of the non-perturbative part are so huge. I remember when many years ago, I gave a talk in Bern, and Schiffman was sitting there, and I was very excited because we were using this pseudoscalar correlator to determine some quark masses. And he said to me, that is all wrong. He said, because, I mean, look at the perturbative coefficients is enormous. Yeah, I said, yes, but I mean, I cannot change it. So, I mean, there will be some systematic uncertainty in this determination, but I mean, it was the very early days, and I was also very young, so, you know. So anyway, so that's the thing. So now, if I should have actually written it, but if you look at the papers, it's written there. They're all the same order of magnitude, if not even. Yeah, the same order of magnitude. That's exactly what happens. You have four terms there, one after the other. So I mean that's meaningless. So what the approximant does is to take that away, and then you have a beautiful convergent series. And then you can use different Padets. I mean, we must make sure that it's not an accident. So we drew X, Padet X, Y, and then change the X and Y, and this and that, and convince ourselves that that is the way to go. And that happens for the light quarks. The coefficients that enter The other charm and bottom, they don't have that problem.
But this is not related to the scheme in which this is not related to the scheme of the heavy core of them.
No, it is related simply to the Feynman diagram. That's what it is. So there is no other explanation.
Other questions?
Well, I forgot when I started. I said that I was the oldest here, or the eldest. Tomorrow I will be a year older. Tomorrow is my birthday. I will turn out a nice number, 77 years old. So, we'll see you.
Thank you very much.
Thank you.